In this video, I'd like to show you how you can write a simple I2C driver to configure an audio codec if you're designing, for example, custom hardware and you need to do the bring up and test out if you can get audio in and out of your digital signal processing system. In my particular case, I have a custom PCB, which we've seen in a number of previous videos, which is specifically for guitar, which uses an STM32H7 microcontroller as a DSP. So this performs all of the digital signal processing tasks, as well as reads in, for example, control settings from ADCs and switches and so on. Attached to this STM32H7 microcontroller, which is running as a DSP, is an audio codec. Codec meaning it contains ADCs and DACs, so analog to digital converters and digital to analog converters. And in this case, this is an audio codec, so these ADCs and DACs are specifically tailored to audio frequencies and to audio bit depths. In this case, this is a Cirrus Logic CS4270, which is a stereo input, stereo output codec, up to 192 kHz sampling frequency and up to 24 bits of bit depth. Quite good, typical hi-fi quality. Of course, there are more parameters such as signal to noise ratio, total harmonic distortion, and so on, which characterize a codec, but these are typical values you will see for audio codecs. In this video, we are specifically interested in configuring the codec using the STM32H7 to set up, for example, sampling frequencies, bit depths, for example, volumes and gains internal to the codec, and just configuring this codec based on the datasheet registers, and datasheet recommendations. For this configuration link, as we'll see, there are oftentimes various different ways of doing this, but in this particular case of this board, this is an I2C link, simply a data line and a clock line that are driven predominantly by the STM32H7, and we can use those to then configure the codec. I2C in this case doesn't have anything to do with the actual audio data transfer, which is achieved via additional I2S lines, so integrated sound, which is very typical for audio data and also has several clocks, and we'll go through that in a bit of detail also in this video, but again, this is predominantly focused on the I2C register config for setting up an external codec. The nice thing is, once you've done this once for a particular codec, once you need to do this for different codecs, you'll see that the setups are very, very similar. There are similar types of registers you just have to set up, similar sequences you have to perform to then be able to stream data to and from the codec and a DSP. If you're more interested in the I2S side of things and how to set that up with STM32s and double buffering, make sure to check out video number 55 on my channel, which goes through exactly that setup for I2S. So I will assume a tiny bit of prerequisite knowledge, and I strongly suggest you check out that video. Link will be in the description box below. As usual, a huge thank you to PCBWay for sponsoring this video. These digital signal processing effects boards for guitar I had manufactured and assembled by PCBWay in China, and they did a fantastic job. For this, I used their PCB prototype service as well as their PCB assembly service. Make sure to check them out, and I'll leave links to them in the description box below. And at the time of making this video, PCBWay also has their 10th anniversary and a couple cool tours and features on their website at the moment. If you'd like to check that out, again, links in the description box below. Before we move over to writing the driver, let's again just familiarize ourselves with the signals that are typically routed out and into a typical audio codec. On the top right hand side, I've taken a screenshot from the datasheet of the specific codec we're using in this example, and we can see a typical pinout here. In my particular case, I'm using I2S to transfer audio data to and from the codec. There are other means and interface standards as well, but this is a very, very generic and very popular interface. The typical signals found in an I2S interface are, for example, the ADC serial data, and this is typically called SD-in or SDTI, and per line, so per trace, so to speak, on a PCB, this carries typically 2 channels of audio data from the codec back to the DSP, the ADC data. Then we have DAC serial data, very similar, except the opposite direction. This is typically called SD-out or SDTO, again, 2 channels per line, this time from the DSP to the codec. I2S, other than the serial data, is a synchronous interface, so we also have several clocks. One is the word clock, or left-right clock, or the frame sync signal. And this word clock typically runs at the sampling rate fs, so if you're running at 48 kHz, the word clock frequency will also be 48 kHz, typically. And the word clock effectively tells us which channel we're currently looking at. So if we're working with left and right channels, if the word clock is low, we are receiving or sending left channel data. If the word clock is high, we are receiving or transmitting right channel data. An additional clock is the bit clock. You'll often see as B clock or S clock, and this typically runs at 64 times the sampling frequency. And the bit clock is there to help the devices trigger on the centers of the serial data. And we can see that on the bottom right-hand side. We have the left-right clock or the word clock at the top. The second clock is the bit clock at 64 frames per second. And you can see the rising edges, for example, in this case, should fall in the centers of our bits of the serial data. That's both the ADC and the DAC data. While not strictly part of the I2S interface definition, you often will find a master clock as part of these clock groupings. And this master clock is synchronous with all of the other clocks, but typically the phase of the master clock doesn't particularly matter. And typically this master clock runs at 256 times the sampling frequency. Now, again, all of these typical values are typical, and there are different multiples depending on what sampling rates you're running at, what speeds you're running at, and so on. And on the top right-hand side of the codec, we can see these I2S signals. So we have SD-in, left-right clock, M clock, S clock, and so on. And that's typically what you'll find on an I2S interface. Other than the I2S signals, we can typically run our codecs in either master mode or slave mode. Typically, at least from what I've seen, codecs will be typically run in slave mode, and the DSP will typically be in the master mode. As we can see from a typical codec datasheet, master-slave mode effectively just determines which device is generating the clocks. So if one device is in master mode, that means it's generating the bit clock and the word clock, whereas the slave mode device is receiving the word and the bit clock. Now, not always the case, but the M clock generation typically requires an external crystal or crystal oscillator. In the case of using STM32H7, you can also use the internal RC oscillator to generate the I2S master clock. However, you will get less jitter, better performance, and better accuracy by using a dedicated crystal. Here, just another slide to illustrate that these master clock, left-right clock, and bit clock, left-right clock ratios aren't fixed. So depending on our speed setting, and the speed setting, as we'll see, determines if we can run, for example, at 48 kilohertz or 90 kilohertz or 192 kilohertz sampling rates, and we can have different ratios between all of these clocks. Other than the audio data, which we have in this case via I2S, we of course have the codec configuration. The configuration, typically for codecs, they might offer two modes. That's either a software configuration or a hardware configuration. And I've taken two images from the datasheet, which we can see in the top right. On the right-hand side, we have standalone mode, which is a hardware configuration. So for example, some of these pins, for example, pin 9 and pin 10, pin 11, and so on, we either tie to a logic high or to a logic low to hard code what mode we're running in. For example, what bit depth, if we're running I2S or TDM or something else, what sampling rate we can determine just by putting these pins high and low. An alternative method, and one I much prefer, is software mode configuration. So now, for the same device, for example, pins 9 and 10 can be used as an I2C interface. And for example, pins 11, 12, and 13 can be used to determine the address of this I2C slave. And this is the mode I typically prefer, and this is the mode we'll be using in this video to configure the device. You can, of course, also have this in an SPI interface or 3-wire interface, depends on the codec you're using. Other configuration signals might be a chip reset or power down signal, which we should also hook up to the controlling device, for example, the DSP. But we can use then these signals in software mode, for example, to set if we're in a master or slave mode. We can set sampling rates, clock ratios, bit depths. Oftentimes these codecs might include certain filters, digital filters, such as high pass filters, low pass filters, maybe volume or gain controls, mute circuitry, frame format, slot sizes, and much, much more. And we'll go through that for this particular codec. Typically, you will do your configuration before you start your I2S streams, but keep in mind some codecs require, for instance, a master clock to be generated before we can do the configuration, as some codecs do go into power down or sleep mode automatically if there's no clock signal applied. Again, my suggestion is, unless there is no specific serial interface available, or you have limited I/O, I would strongly suggest to go with software mode for flexibility and for debugging capabilities. The actual hardware connections I have on this particular board are shown here. This is a snippet of the codec schematic. I have my serial audio interface, in this case I2S, connected to the I2S lines of the codec. I have an I2C hooked up, as well as a codec reset signal, which is active low. Other than that, I've tied the address pins via pull-down resistors to ground to give a certain I2C address, and we'll go through the codec datasheet in just a second. And these connections will be very, very similar across many different codecs. Before we move over to the datasheet and then implementing this in C, in software, let's look at typical configuration steps that you'll pretty much always have to do anytime a codec is involved. Step number one is, of course, that once you power up your board, the power rails come up, and you would, in most cases, have a pull-down resistor in place on the end reset or in power down lines if your codec has one, to make sure the codec doesn't boot up by itself. Then your DSP or microcontroller, whatever processor you're using, initializes. We will configure the I2S interface in the DSP, or whatever interface you're using to transfer audio data, and if necessary, start the I2S clocks. Again, this depends on the codec you're using. For configuring I2S, that's to do with frame format, sampling rates, bit depths, how many channels you have. After that, we then configure the I2C or the SPI interface, whatever we're using to set up and configure the codec. Once all of this initial configuration is in place, the DSP, the processor, then cycles, then reset all the power down pins to make sure we can then talk via a serial interface, via I2C or SPI to the codec. Then we can perform the actual configuration of the codec. Quite simply, the usual way we do this is we check the registers from the datasheet. For example, here, the device we're using, I've pasted in the register quick reference guide on the right-hand side. So we go through each one of these registers, or to minimum, just the specific ones we need. We'd read the codec registers, toggle the bits depending on config, and we have to watch out for some reserved bits, and we'll see this in just a second. Once we toggle the bits, we write back this adjusted configuration to that specific codec register. And then finally, we read back that written value just to verify that we actually wrote that value to that register. Again, just like a double or triple check. The order of configuration, of course, can be important. For example, some codecs require that it's actually powered down, at least the software powered down, before you make any changes, for example, to volume controls or I2S configurations, before you then power the device back up again. So the order of configuration is something to keep in mind for any codec, and this does in fact vary depending on what codec you're using. After you've looped through and you set all the registers, you power the codec up completely, you can then begin running your processing loop to process and retrieve and transmit your audio data. And that's from that previous video, video number 55, which goes through the I2S and DMA streaming. So now let's move over to the datasheet and STM32Cube IDE and look at how we can write such a simple driver. Let's briefly familiarize ourselves with the typical datasheet for one of these audio codecs. The first page, as is usual with datasheets, gives an overview of this codec. This particular one is up to 24 bits bit depth, up to 192 kilohertz sampling rate, and it's stereo. We can read about the dynamic range, distortion and noise performances, and what audio interface formats are available. For example, left justified, I2S, and right justified. It also includes, for example, a de-emphasis filter, pop guards, volume controls, high-pass filters, and more. And this, of course, depends on what codec you're using, but this is quite typical and quite a simple codec for us to explore. If we go to the pin descriptions, page 4 of the datasheet, we see that we have a software mode pin description and a standalone or hardware mode pin description, as we saw in the slides earlier on. And we're using software mode, so that's why we would have this first pin out. Then, as usual, typical connection diagrams, and also descriptions of the various interface types we can use, left justified, I2S, and more. Importantly for us, we will be jumping to section 5, the applications section of this datasheet, talking about standalone mode and serial control port mode. What we're using is serial control port mode or software mode, and we can see section 5.2.1 already tells us quite a bit of information. So that power up achieve is by keeping the device in reset, again with this pull down resistor which we saw, until the supply pins are stable, and then we release and reset, so pull it high to power up this codec. Then after an reset is released or pulled high by our DSP in this case, we actually have to set the power down bit to put this device into serial control port mode. And if we don't do this within a certain number of sample periods after the release of reset, the device enters this standalone mode. So this is something we have to keep in mind for the driver. We have some more talk about master-slave mode, again, who's generating the clocks. Then with regards to system clocking, this particular device has 3 clock modes: single speed, double speed, and quad speed. And effectively, this is just talking about the sampling frequency. So if we're running at typical audio sampling frequencies, we would be, for example, at 44.1 kilohertz or 48 kilohertz, and we would just stick with single speed mode. Otherwise, if you want to go with 96 kilohertz, we'd have to go with double speed, or 192 kilohertz, we'd have to go with quad speed. Depending on what sampling frequency and sampling rate you want, you'll have to then also look at the clock ratio selection. With single speed, we have different master clock to left-right clock ratios than we have with double speed or quad speed, whereas the bit clock to left-right clock is always fixed at 64, and the left-right clock itself is also fixed at the sampling rate. We will come back to these tables because you can see on the right-hand side we have these various setting bits, master clock frequency 2, 1, and 0, which we have to also configure in the registers to put this device in single speed, double speed, or quad speed mode. Following on from this section, we have more information on, for example, if you want to do digital loopbacks, muting, using the high-pass filter, and so on. So we will be referencing these sections once we go through these registers. Section 6 tells us more about software mode, how, for example, the I2C control works. So, for example, the slave address is 10011, but this is followed by the address pin settings. I've pulled all of my address setting pins low, so it's 3 times 0, so we have an address of 10011 followed by 3 zeros. We can see typical frame formats for I2C or SPI if you'd like to use that instead. Now, importantly for us, what we're going to do is go through these registers and figure out what bits we do and we do not need to set. Codecs will typically have a register quick reference, which lists the address of the registers. So we have 1, 2, 3, 4, up to 8 in this case. So a pretty simple device, and what the bits in each register do. So for example, the first register at address hex 01 gives us the device ID and the revision. Then for example, the power control register at address hex 02 gives us other bits such as the freeze and these other bits here, as well as some reserved bits which have to be kept, for example, in this case, at 0. If you'd like to get more information on the individual registers, and that's definitely something we'll need because we can't really guess what the freeze bit does just from this graph, we can always scroll down or click on where the power control register is explained in more detail, in this case page 32, and this tells us then about the individual functions of all these registers. For example, the freeze bit, bit 7, has a description like so. So in this case, what we actually have to do is quite straightforward. We have to make sure that we do a proper sequencing of these registers. Remember, to go into software mode, the datasheet tells us we have to write the power down control register bit, and then we can start setting all these other registers, but then we would go through and set our default configurations for all these registers, and afterwards we can then run our I2S processing functions. Jumping over to STM32 Cube IDE, let's look at the basic configuration of this microcontroller. If you've watched the I2S Config video, you'll be familiar with SAI settings. In this case, I've set the protocol to be a I2S standard protocol with a data size of 24 bits, both for the ADCs and for the DACs. 2 channels, and an audio frequency in this case only at 32 kilohertz, because this is for guitar effect pedal. I don't need particularly much bandwidth. We need to keep this in mind because we need to set the I2S standard, data size, and audio frequency, and we need to configure the codec correctly. Other than that, for my configuration interface, I've just selected I2C1, which is hooked up to the codec I2C lines, the clock and data. I'm just running in standard mode, just 100 kilohertz. We're not doing at all much data transfer, so we just use standard mode. Let's go through the driver now and see how it's put together. Keep in mind this is a pretty simple driver. It's particularly tailored to my needs of this guitar effect pedal. There are certain things you could do to make it more modular and adaptive, but this is the bare minimum to get one of these codecs going. I've defined references to my I2C handle, so this was I2C1, and references to where my GPIO port is located for the reset signal. Then we have the I2C address, and this was again defined in the datasheet, which happens to then translate to hex 48, but the 8th bit is actually the read-write bit, as is typical, so we have to left shift this address by 1, because the 8th bit again is used by the read-write bit. I've defined the various register addresses, and that's simply taken from the register quick reference, and we just have 8 registers, device ID all the way to the DAC channel B volume control 1 to 8. So that's all I've transferred here. I also have this device ID defined. If we jump to register number 1, we'll need this just to verify that we're talking to this device correctly. We can see bits 7 through 4, so the most significant 4 bits are equal to hex OC, so therefore later we'll mask the whole register and check for that value. What we'll actually be using to set the register configuration values, or the default values, is just an array where we have 1 value per register. I've defined a reference to the I2C handle, and then we have our functions. We have our main initialization function, which will set up the codec, loop through the registers, and set the values we want. I've got a reset function, which simply just toggles or cycles the end reset pin, and I've abstracted a tiny bit the hardware abstraction layer functions, so I have specific ones for this codec register write, which is a single register write function, and a register read function, which is a single register read. Jumping then over to the .c file, we have the codec reset function, which effectively just toggles the end reset pin, so pulls it low, waits a certain amount of time, pulls it high, waits a certain amount of time, so we do this somewhat hard reset. Keep in mind you will typically need a delay, specifically after you pull the device out of reset and power it up, for the device to be ready and to be able to accept commands, for example in software mode. Then I have my abstracted register write and register read functions, and for these I'm just essentially filling in the HAL I2C mem write and HAL I2C mem read functions, passing the I2C handle, the I2C address, what register address we want to talk to, and then the register data, and that we want to read or write 1 byte. Essentially just a single byte write and a single byte read from the specific address using the register address we pass to this, and either writing or reading a register data from or into that variable. With that in place, we can actually then look at the configuration function, which is essentially this initialization function. And always you should reference the datasheet of what the actual structure is, how this needs to be configured, in what order things need to be configured, how do you perform the resets, how do you get this into software mode. All of this is documented into the datasheet, and while this is very similar across codecs, there are some minor differences between codecs that means this approach might not and will probably not work for all. So always make sure to follow the datasheet and their recommendations. Their recommendation was to do a hard reset of the codec using the end reset pin, and then we want to put the codec in power down mode, which puts this also in software mode as we saw when we were scanning through the datasheet. So I'm writing a single register to the power and control register and setting certain values. This is hex A3, and let's see why. The power control register has these number of bits. We have a freeze bit, reserved, PDN ADC, 3 reserved bits, PDN DAC, and PDN. To get this into software mode, we saw that we have to set the PDN bit high. The rest doesn't really matter. But I will enable the freeze bit, and I will power down the ADCs, and I'll power down the DACs, and I'll power down the entire system. Keep in mind, for this particular power down, we can still write to the registers of this device. So in certain codecs, when you perform a power down, you may not be able to write to the registers, but in this case, this does work. So I'm going to set the freeze bit, PDN ADC bit, PDN DAC bit, and the PDN bit. So in binary, I've written at the top, we wanted 1. Then the reserve bits in this particular case, as we saw from the register quick reference, every time we have a reserve bit, this needs to be 0. And this might be different for the particular codec you're using. You might have to check the state of the reserve bits and then do a bit mask instead, rather than writing fixed values. But in this case, we can write fixed values of 0 every time we have a reserve bit. So therefore, we want freeze 1, reserved 0, PDN ADC 1, 0, 0, 0, 1, 1. So this is the binary value we have at the top left, 1010, 0011. And that happens to be hex A3, and that's the value I used to put this codec in power down mode before we do any further steps. Then I check what this I2C transfer function returns. If it returns a timeout or busy or error, then we jump out of this initialization function. But now, after the hard reset of the codec and putting the codec in power down mode, we can now adjust the configuration. And typically the first thing I will do is check the device ID. The device ID we saw is actually register hex 01, and we want the top 4 bits, because those top 4 bits are fixed, to be 1100, whereas the lower 4 bits are the revision, which might vary across device, but we know that ID 3 to ID 0 are fixed. So therefore, I'd like to read that register, so I do my register read function with the address of hex 01, and I pass into that an 8-bit wide variable, which will then contain this register information. So I perform register read, place information in the device ID, and then I check the top 4 bits using this bit mask, and to check if that's the same as the device ID, which is hex C, which is 1100. Now that we've checked the device ID, let's just verify that we're working so far, that we've performed the hard reset, that we can put the codec in power down mode as suggested by the datasheet, so we can actually put this in software mode, and then we check the device ID. So I'll set a breakpoint at line 35, and in main.c, all I'm doing is I'm including my codec header file, my codec driver, and in int main, after initialization of the serial audio interface, the I2S streams, I'm initializing the codec with this call. I've got an ST link connected to my board, and I've powered this up. We've got a breakpoint set, so I can click debug, and now let's see if we reach that statement, and let's see if we get the correct device ID out. So we have a breakpoint straight from main. Let me click resume. Okay, we've landed the breakpoint. We can check I2C status by hovering. That's HAL OK. And let's check what device ID we've read into this register, and that's hex C3. Remember, we are only interested in the upper 4 bits, which is 1100, which is hex C, which is equal to our device ID. So this is great. This looks like it's working so far. Now we can actually move over to setting up the codec registers. For setting up the codec registers, remember we have 8 registers here. I've put in just an array of bytes which have our desired values for these codec registers. And again, this is just following the order from the register quick reference. So the first is device ID, then we have the power control, mode control, and so on. And these values I filled in here, I've calculated or set depending on what bits need to be set in these various registers. We'll go through why we chose these certain registers in just a second, but let me just go through how these are then actually written. So we loop through all of the registers, and I'm actually starting at the last register, hex 08, and I'm looping down back to the power control register, because the power control register is the last register I want to write to get this codec out of this low power state and power up the ADCs. Remember, the first thing we did was actually power down the device, power down the ADCs, put this into this low power mode while we're adjusting the configuration. So the last thing we want to do after we set the configuration is get it out of this low power mode. So therefore I'm starting at the last register and moving through a loop back to the power control register. The way I'm then doing that is writing to the current register index, whatever the configuration settings were at that particular index. Then I'm reading back the register value just to confirm, and if it's okay, I loop through to the next register value, and after that we've actually configured our codec. So what we need to do with this configuration is figure out what values we need to put into our default settings. So let's go through these registers. Let's jump to the datasheet and look at mode control, register number 3. And for this, we have the first 2 bits are reserved, then we have FM1, FM0, this master clock frequency settings, and pop G. And again, the datasheet will explain everything. FM1, FM0 determines the speed mode as well as if it's master or slave mode. So if we're in master mode, this will determine single, double, or quad speed, but we are running this codec in slave mode. Therefore, the clocks will be generated by the DSP, by the STM3287, and we want to select slave mode. Remember, the reserve bits are 0, so the first 4 bits are 0, 0, 1, 1, 2 reserve bits of 0, and then FM1 is 1, and FM0 is 1 as well to put this into slave mode. Then we have 3 bits of clock frequency, and this is the ratio select bit. And these are used to set the clocking ratios, and the default is that all of these bits are 0, which gives an M clock divide by 1. If we jump to the clock ratio selection section, 5.2.4, we can see and scroll a bit down to slave mode. We want to define our M clock frequency bits depending on if we're single speed, double speed, or quad speed. I'm running this at 32 kilohertz, so I am in the single speed range. My master clock generated by the STM3287 has a fixed ratio of 256 times the left-right clock. So therefore I want this first setting here. So I want 0, 0, 0 for all these M clock frequency bits. So therefore, we can have 3 zeros, and then we just need to set the last bit, which is pop G. So let's scroll down, and that's a pop guard transient control, and we can read the description here. And this sounds quite useful. It helps reduce the effect of pops when we're turning on and off this device, so I'll set the last bit at 1. So therefore, we've got the register contents of 0011 followed by 3 zeros and 1 1. That gives us hex 31. And hex 31 is exactly what we have for this particular mode register. It's in slave mode. We have normal or single speed, and we enable the pop guard. So that's why I have register value number 31 here. And in this way, we would go through the remaining registers in exactly the same methodology. The next register is the ADC and DAC control. And here we can enable or disable the high pass filters, the digital loopback, the digital audio interface format. So in my case, I don't want a high pass filter, so I'll set the first 2 bits as 0. I don't want a digital loopback, so I'll set that to 0 as well. But I do want to set the DAC digital interface format to be I2S, because that's what I'm using in my case. So I want bits 0 and 1 for DAC diff 1 and DAC diff 0. Then we have 2 reserve bits. They have to be at 0 and 0. And then we have the ADC diff 0, which is the digital interface format. So we can choose between left justified and I2S, and I want I2S, so I have a 1 there. This gives me register contents in binary of 4 zeros followed by 1001, and that in hexadecimal is hex 09, and that's exactly what I have here. Then I would continue that process, for example, for the transition control register, for the mute control register, and the volume control registers. Very, very similar process, figuring out what bits I need to set and which I don't need to set, watching out for reserve bits and writing them to the registers, and then reading them back just to verify. Now, of course, you don't have to do a single register read and register write. You could do a block-based read and block-based write. It depends on how you set up your driver. Keep in mind, this is a very, very simple driver. So what I could do, let me just set a breakpoint line 61. Let's upload this code and debug and just check that all the register contents are as they should be and that they're being written to and read correctly. Then I click resume, and we want to make sure that reg data that's being read back is the same as our configuration data. So we want to make sure this top value equals the bottom value for all the registers. So we're reading, writing, and making sure that all the registers are coming back. And hopefully with everything read back and configured correctly, we can return 0 and end our initialization function and click resume. And now the codec is correctly configured and we're running our main processing loop. So I can set a breakpoint in the process half buffer function, and we can see our codec is being configured because we're getting input data and setting output data. If you'd like to see this codec driver in action, you can see this across various different videos on my channel. For example, the previous video on real-time FRR filters uses that driver, or when we're doing a QA403 audio analyzer tutorial looking at noise, SNRs, total harmonic distortion and so on, that's using that driver, for example, the impulse responses. So this driver has been utilized on many, many different systems, and make sure to check those out. This driver, of course, is very, very simple. It covers the absolute basics. If you'd like to see a more extended driver, in the Linux repo, they actually have a driver for this particular part, and you can see how, for example, a professional driver is written with all of the defines and bit masking. If you want to make this driver far more flexible rather than just having one, for example, standard configuration, I'd strongly suggest checking this out, and I'll leave a link to this in the description box below. In any case, I hope this video was helpful. I hope it showed you how you can quite easily interface with codecs and configure them just by going through the datasheet and paying attention to the register setup. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date to any latest firmware, DSP, hardware design, and PCB design videos. Thanks again for watching, and I hope to see you in the next one. Bye-bye.